Hi everybody. So we've talked about feedback loops, and now we're going to get into the nitty-gritty of using the data that we found and putting it and applying that data to some theories to see if the theories fit with the data and can explain some of the events that happened in the past that produced climate change. And in doing so, then we might be able to predict what's going to happen in the future with the same theories. So let's look into that. The first one we're going to look into are changes due to solar radiation. Then we're going to go in through changes in atmospheric components and changes in the Earth's surface. But we're going to spend quite a bit of time on changes in solar radiation. And to do that, we're going to talk about the Milankovitch theory first. This is a natural circumstance of what happened with the Ice Age and the glacial advances and retreats back hundreds of thousands of years ago and tens of thousands of years ago. So we're going to explore that theory and see if it applies today as well. The Milankovitch theory is a combination of three known cycles that were known to the Greeks. And these cycles were then used by Milankovitch, a Serbian astronomer, to explain glacial advance and retreat in the past. And he used those three cycles because one of them has to do with the distribution of sunlight, another has to do with the location of sunlight, and a third with the timing of sunlight that can hit Earth. So it can explain when these three cycles merge. It can explain glacial advance and glacial retreat. This was in the 1930s that this theory was postulated, and it was promptly ignored. Nobody paid any attention to it. And then in the 1970s, Dr. Cousteau started to do some research into ocean sediments and supported some of the work that was done to look at the fact that, hey, this theory might just be right, with some of the same methods that you saw in the previous videos for dating sediments. The theory that Milankovitch was trying to explain was the retreating of the ice sheets. And he was noting that when those ice sheets retreated, and melted off, they flooded the oceans so that the entire world lost 200 feet approximately of coastline, which is a lot of land to lose when those sheets melted. I decided to put this information into a chart, which I hope that you'll come back and use. It's a chart that I use to remember the theories and to explore them and to learn more about them. There are three cycles in this theory. One is the eccentricity cycle, another is the obliquity cycle, and the third is the precession cycle. This chart is for you to come back to, and it also helps me to remember things. What I want to explain to you is that the Earth moves in three different ways. We'll go over that. And then I remember this I usually use songs to remember things. So I think like all about the base. So all about the shape, all about the tilt, all about the bulge. You can sing it yourself. If you're a visual learner, you might want to go and remember these visual cues. And then there are vocabulary cues as well. All right. So we also talk about what these cycles are caused by and what they result in. They result in differences in the amount of sunlight, the location of sunlight, the timing of sunlight. I have some issues with the way this information is presented in the book. I present it slightly differently, and hopefully it'll make more sense to you. So the Earth moves in three different ways. It rotates around an axis every day. It revolves around the sun every year, and it precesses, which means it wobbles around its axis while it is in orbit. Let's go over the revolution movement as well. Revolution is the motion of a body around an inside point. Now, just a second ago, I talked about the Earth revolving around the sun. And actually, the Earth does not revolve around the sun. The Earth revolves around a point on the outside of the sun, and the sun revolves around the same outside point. So the sun actually revolves around its exterior once every 27 days, something new to learn, and the Earth revolves around that point once every 365 days. And this is the orbital motion that we were talking about. When we get to precession, precession is the motion of a body around a force. And that is why we start with what you know. The top wobbles around gravity and friction forces that really key in on its bulge right here. So the tops that last the longest by physics are the tops that have a really prominent bulge. And gravity pulls down on that bulge, and friction slows down the angular momentum of the spin. So that wobbling happens very rapidly on a top. Now, you can think about wobbling in another way too, in a pregnant woman. And I've been pregnant, so I can say this, okay? A pregnant woman wobbles around a new gravitational bulge out of her abdomen. So a woman will wobble around that center of gravity that has changed. Bring to mind that bulge and keep it in mind for the Earth. The Earth actually wobbles around a bulge at its equator that's caused by the tidal pull of the sun and the moon, so that the equator is actually about 43 kilometers wider than the same measurement from pole to pole. The equator is making this a little bit of a distorted sphere for the Earth, and that wobble really impacts the rotation of the Earth around its axis. To go back here, we're going to explore how these three cycles work with the three movements of the Earth. For instance, the eccentricity cycle moves with the revolution in the orbit, the annular revolution of the Earth. And the eccentricity cycle talks about the shape of the orbit. It actually says that the shape of the orbit is not a perfect circle the vast majority of the time. It's just a little bit off as an oval. That's what we're going to explore next. This is a 100,000 year cycle of going from a circle to a bit of an ellipse, a bit of an oval, and back to a circle again. And at its most, I should change this, it can get up to about 9% difference between a circle and an oval. Very hard to see, but about 9% difference due to the pull of Jupiter on the Earth at certain parts of its orbit. Jupiter has a massive gravity and actually pulls on the sun quite a bit. As a result of this pull and this eccentricity, you end up having seasons that are a little bit different in their intensity. The solid line is the movement of a circular orbit where seasons would have the same amount of radiation throughout the orbit. If you are in a more elliptical orbit, you're going to be farther out from the sun here, and you're going to be closer to the sun here. We are closest to the sun in January, and the southern hemisphere gets more sunlight than the northern hemisphere during their summer. As a result of this, we are closest to the sun in January. We are farthest from the sun in July on account of our eccentricity, which is now right around the middle to low, about 3% eccentricity now. And we're trending toward less eccentricity and more circular orbits in the future for more even heat. Does this have a relation to climate change now? I mean, it did have a relation to climate change when the ice sheets were over the Earth. Does it have a relationship now? No, it does not, because our climate is changing quite rapidly over the past century, and this is a 100,000-year-old orbital cycle. It doesn't have a relation to this. Let's go to the second cycle, the obliquity cycle. Now, obliques, what is an oblique? Well, think about it. You think about the obliques as the muscles on the side of your body. These muscles actually have a slant to them. They slant from the lower abdomen up to the thoracic cavity. And as a result, obliques are slanted muscles. The obliquity cycle is the slant that the Earth has on its axis. The Earth does not rotate from a perpendicular axis. The Earth actually rotates on a slanted axis. The slanted axis can go on a tilt anywhere from about 22% to about 24.5%. We're going to explore that change from 22 to about 24.5% and its impact on the location of sunlight in the hemispheres. So let's get to that. And that is on a 41,000 year cycle to change the axial tilt of the Earth. Now, the cause of that, the original cause of that, is theorized to be a massive, literally massive collision 4 billion years ago after the formation of the Earth during what's called the Great Bombardment of debris from the formation of our solar system. And in that massive collision that threw off the axis of the Earth from vertical, it actually was a blessing because it gave us differential seasons. When you are looking at the Earth here, you are seeing that the northern hemisphere is getting more light than the southern hemisphere, and there is more light for the northern hemisphere in the summer, less light for the northern hemisphere in the winter. It's really the reason for the season, this obliquity cycle. Right at this point, we're at 23.4 degrees off vertical, and we are trending to the 22%. It's going to take us a good 10,000, 15,000 years to even get close to that lower tilt. And as we do, there's a predicted ice cap expansion because of what we know from our sediments on what happens during this cycle. Is this change that we're noting related to present climate change? No, it is not. This is a change, again, that happens over tens of thousands of years, and our climate change is evolving quite rapidly within a century. So while this theory worked for the ice sheets, it's not working for our climate change right now. We are going to get to precession, that's the third cycle, on the next video, and we have a lot to talk about there. So I will see you on the next video.